Okay. It's a great pleasure that we have Dr. Bedrich. Bedrich, is my pronunciation correct?
Yes, it almost is.
Almost. Okay. Dr. Beneš is currently a professor and associate department head of computer science at Purdue University. He earned his PhD from Technical University in Prague in 1998. And Dr. Beneš is a fellow of European Association of Computer Graphics, which is Eurographic abbreviation, and also a senior member of ACM and IEEE. He is currently editor-in-chief of Elsewhere, a journal of graphical models, and previously served as the paper chair for Eurograph 2017. His research focused on generative method for geometry synthesis and deep learning, and he has more than 200 research papers and received funding support from prestigious organizations such as NSF, NASA, Adobe, Intel, Siemens, Samsung, Department of Energy, and Ford, and many others. Dr. Beneš is also a faculty scholar at Purdue University, and it's really our great pleasure to have him to give the talk. And his talk title is "Can AI Help with the Reconstruction and Digital Twins of Vegetation?" Thank you very much, Dr. Beneš. You can go ahead, I think.
Thank you, Professor Lu, for a nice introduction. I really appreciate it. Let me start sharing my screen. Can you see my screen?
Yes, we can.
Okay, perfect. Thank you. So yeah, I really don't like online presentations because I have jokes and people don't laugh, so I have no feedback. So I hope that it will be understandable and enjoyable. The title is if AI can help with reconstruction of vegetation and with construction of digital twins. It seems that these are two topics that may not be entirely related. I will try to make the case that they actually are related very much. And I believe that the reconstruction is essential step for digital twins. So vegetation is important, and I am coming from the viewpoint of computer science, not from the viewpoint of biology. And interestingly enough, in computer science, we have studied shape and color of plants for more than 40 years. It's probably getting close to 50. So there were many algorithms that were trying to capture how plants grow, how they change color. There were algorithms for physics simulation and so on. So we are definitely not starting from the scratch. And if you want to work in this field, there is a lot to study and a lot to learn. Now, there are some things that are definitely new. So one really important new thing is that we have tons of new sensors. We have LiDAR, we have high definition cameras, we have depth cameras, we have infrared, we have near infrared, we have, ultrasounds that can measure roots under the soil and so on. So this is definitely something that is new, that enables many new things that were not possible before. And consequently, we have a huge amounts of data. And if I say huge amounts, I mean literally petabytes of data that are, sitting on repositories and they're just waiting for being used. If I get a dime for every time somebody says, "Oh, we have a drone and we fly it over field," then I would probably be a millionaire. Another important thing is, and this is the third thing, is that we have machine learning and AI-based algorithms, as everybody is aware of. So if we take these three ingredients, the three new ingredients, and we take the previous work in computer science and biology, then we are really getting close to having digital twins of plants. And the digital twin is a copy of a real object. I can take this pencil and I can make a computer model, and then I need to have a way of model it. So what I can do, I can try to break it virtually in the computer. And the typical, important thing for digital twins is that we have the real object and we have a streaming data. So we continuously, or with some delta t, we measure the real model and then we update the computer model in real time. So what I'm trying to make here is an argument that we are getting close to having digital twins of plants The digital twins started in computer-aided design, in I believe this was NASA that had, virtual models of their spacecrafts and so on. Now, if we have digital twins, then it would, theoretically have a huge impact into many disciplines. We could play what if scenarios in architecture. We could take a city and populate it with different trees. Uh, in biology, we could start virtually, making experiments with plants in different climate conditions without actually waiting for them to grow because the digital twin could grow actually, very quickly. Of course, in agriculture, etc. Another important thing is that, we could affect genetics in this, and I will show some examples. We could, work on livable cities. This is example that I've mentioned. And for me, probably the most important one is that we could generate, better understanding of nature. This is, what in these days is called AI for science, when you take the artificial intelligence models and you try to answer some, important research or scientific hypothesis. So this is the motivation for this everything. This is the structure and the take-home message. I will first talk briefly about plant models. Then in the second part, I will talk about small plants. It goes by size. So I will talk about small plants, digital twins. I will show some use cases and some important lessons that we learned. In the third part, I will go into trees and I will show some advances, and I will show some advances where artificial intelligence actually was essential. And then I will go to conclusions. And the take-home message is that computer science is essential in modeling vegetation for science. I believe that, people in biology and ag can really benefit from what people in computer science do. And I believe that people in computer science really need biologists and people in agriculture to learn something, about the way we model these things. So let me move to the first thing. Plant models, and I don't want to really dive deep into this. I am talking about the 40 years of research. They have basically three important parameters that allow the modeling. One are geometric parameters, such as branching angle, width of leaf, length of internode, and so on. Now, plants grow, and they typically grow by bud development. So we need to have also parameters for bud lifespan, how bud reacts to internal uh, sensing of hormones within the plant, and so on. And probably the most important third set of parameters are environmental responses, how it reacts to sun, to different temperature, to gravity, to proximity of other plants, what happens if you prune something, etc., etc. So let's assume that we do have this model. Then what we can think about it, we can take it mathematically, and we can look at the plant model as something that generates three-dimensional model based on the set of input parameters. Now, the important thing is that once we cast something into the set of input parameters, it will always generate valid three-dimensional structure. It doesn't need to be valid plant because the leaves can be crooked or very long or very short, but it will always be perfect three-dimensional structure. Now, here's an example of parametrization of sorghum where we, worked closely with people in agriculture and we parameterize, the leaf into sheath, auricle, width, blade arc length, blade length, and all these parameters were exposed as was in the previous slide as a set of parameters P. Then what we did, we took, several of these leaves and put them together into three-dimensional model, and we ended up with a hierarchical geometric model. We also simulated reflectivity and the panicle and everything. So once you add time to this everything, you end up with a model that is capable of simulation of growth. And as I said, I don't want to go too much into details of this. Let's assume for now that we have this model. Now, what you can also do, you can take this plant. You remember that I mentioned the environmental parameters. And what you can do, you can create virtual three-dimensional field in which you can walk and the plants actually compete for space, for resources, and so on. So going back to what I mentioned before, we have a plant model, we have a set of parameters, and the plant model has some generation engine, that generates three-dimensional model on the output. We run the same exercise in 2021 for trees, and we also have a developmental model of trees where we can simulate different species fully in 3D. They grow, they compete for space, they compete for resources, etc. Okay, so this was the plant model. I apologize for not providing too many details, but I want to get into things that are more relevant to AI. So let's move to the part two when we talk about the small plants. And the digital twins and how to make them. Uh, so I already mentioned that we have the parametric model. Now, if we want to make a digital twin, that means that we have on the input three-dimensional plant or some kind of data that capture the plant. And there is something, this is the question mark, that gives us the set of parameters. And now this is really important to distinguish that in this approach that I am trying to propose here, we need to have the plant model first. And then the digital twin is modeled through the set of parameters only. That seems as a simple exercise, but finding the set of parameters that provides the exact model on the input can be very complicated. Now, if we want to do this, of course, the most important thing is that we need data. And I also want to make one important distinction is that the traditional computer vision goes from input data directly to the three-dimensional model. There is usually no or not very strong assumption about the underlying structure. Sometimes we can say, that the structure is branching or that, they are tiny leaves or thin structures and so on. But usually in computer vision, we just take input data and we try to extract as much information directly without having strong assumptions about the underlying model. In this approach, we have extremely strong assumption. We know that it's a plant, we know what species it is, and we know what are the parameters, and we are trying to find the parameters. So one thing that we did is that we took data from phenotyping facility at the University of Nebraska. Phenotyping facility is a greenhouse where the plants are sitting on conveyor belt. There is a operation center that is, chair with a computer. And when you press the button, then the plants start moving and they get into the phenotyping, they get into something that is called imagining chamber. And they get there one by one and multiple images are taken. The images are typically taken in RGB, sometimes in infrared, in multispectral and so on. So the output of the pass is that you get something like 6 images from 5 different sides and from top of the plant. Now, what we did in this experiment, building the digital twin through the reconstruction, is that we used something that is called voxel carving algorithm. This was a paper in 2020, and we basically project the 5 images, the 6 images, also the top view, onto the voxel model, and then we found which voxels are visible and which are not. And we ended up, with some kind of skeleton that later was fit, and we ended up with a 3-dimensional model that looks like this. There was a lot of manual tweaking of the input parameters to get everything right. And then eventually what we did, we took 230 plants from the phenotyping facility over several weeks of growth, and we ended up with a set of parameters that correspond to the real plant. And this is really important. It means that every parameter that we had was represented as some kind of Gaussian distribution. That was the branching angle of the leaf one was something plus minus some variance. Now, the really important thing is that if you take the set of random, if you take the input parameters and you throw a random number that fits the measured set, then you end up with a natural plant model. So you end up with a valid 3-dimensional model that doesn't need to be a plant that was in the input data set, but it's plant that has the same distribution of parameters as a real plant. So we validated it. It's in the paper. I don't want to spend much time on this, but the important thing is that with this, we can generate very realistic synthetic data. We just throw random number into the set of parameters and we get 3-dimensional models. Now the question is, can we do something useful with this? we have a model that corresponds, to digital twins, to geometric digital twins of large, if 230 is a large data set of three-dimensional sorghums. So let me talk about the use cases, how this was used. Now, one really interesting thing, and this is my message for the collaboration, is that, in computer vision, we care about, perfect three-dimensional reconstruction. If there are holes, if the objects are disconnected, then we consider this everything as a failure. So we were, working on the three-dimensional reconstruction, and then our collaborators came to us and they said, do you know the branching angle? And we were quite surprised because, of course, we know the branching angle. It's, extremely simple thing that we already had, on the hard drive. So they asked us whether we can reconstruct additional 1,092 plants. So they run, different experiments. We took the data, we reconstructed it. And then in one afternoon, a very talented PhD student ran this everything from genome-wise association study. And now I'm getting into a field that is not mine because I'm in computer science. But if you know the genome of the plant, and if you have enough data, then this algorithm allows you to find statistically gene that controls the particular trait. So this was really exercise for one afternoon, and it turns out that on chromosome 7, there is a gene DW3 that controls the branching angle, and we were able to extract it from the data. In the subsequent study, and this was last year, we used exactly the same algorithm for 3D reconstruction, for skeletonization, and we were able to isolate a gene for phyllotaxis that is sitting somewhere on the chromosome 5. So once you get this data, you can do really interesting things, but you really need to communicate with your partners because we were not aware that something like this can be done, for the plants that know the genome. This was use case one. The use case two is, as I already mentioned, we can generate synthetic data. Now the question is, can we do something useful? So one of the very common things in this world, of procedural modeling of plants is that we can generate synthetic data. So what we can do, we can take, this is, by the way, a procedural model that was generated by casting the random number into the set. And then what we can do, we can say, okay, let's render every leaf in different color. Now, if you look at this image and you count the number of colors that you have in this image, minus background, stalk, and the pot, -3, then you get the actual number of leaves. So also, we took, our generative model and we generated pairs of photorealistic images rendered, with by bidirectional path tracing and photon tracing and colors and reflectivity and everything. And the second image was just color-coded index color images that were used for counting. Then we trained, simple pix-to-pix deep neural network, and then we basically used it by providing it with the real data and measuring the leaves. There was a interesting observation. We had ground truth data that were captured by human observers. Now, every time we compared to ground truth data, the pix-to-pix was 3 leaves off. So we were coming back to the deep neural model, checking everything, scratching our head what is wrong. And then eventually we got, the good idea to have a look at the human measurements. And turns out that people are not really good at counting leaves. So they could differ up to 4 leaves on a single plant. So what we eventually did, we, talked to statistician and we create a statistical model of a human computer, of a person that is calculating it, that gave us the distribution, and turned out that the AI-based model for leaf counting was fitting really well. So often we say that, ground truth is something that is counted by humans. There are actual methodologies on how to avoid errors in human counting, but I just want to make you aware that, these errors can be quite significant. So lessons learned. The good is that if we have carefully defined observations, meaning the developmental model, and we have measurements, then we can get to some approximation of digital twins. we can get really, really good 3D reconstruction if we know the exact conditions, such as in phenotyping facilities. And we can actually get quite interesting applications in different fields by just running, the simple traditional computer vision exercise. Now, the bad thing is that most of the plants don't grow in phenotyping facilities. I would actually say that almost all plants don't grow in phenotyping facilities. Now, plants in the wild, they interact with each other. That has a huge effect on their shape. This is one important observation. The second thing is that the data acquisition in the wild is extremely difficult. If you ever look, at the cornfield, then just isolating, having segmentation of individual plants is extremely difficult problem. Now try to segment leaves. And we do not have digital twins of field plants yet. There are, some approaches. And the interesting thing is that plants of this kind are actually rather small. And that means that if you take a picture, then you have a high information density during scanning. You have a lot of information there. So now let's talk about trees. The trees are much taller, much more complicated, and using the same scanners, we have a way less information in this. So I will talk about big plans and some advances. There are many developmental and interactive models in computer graphics. These are some examples that my collaborations and myself did. This is from 2012 when we have trees that automatically adapt to environment such as if they were grown in that environment. So you can see competition for resources, self-thinning. Uh, we have a quite advanced physics-based models that allow trees to interact, with wind, with each other. We can break the leaves. This was example of a tree growing under very, very strong influence of wind from one side. We can simulate interactively in real time. In real time, it's questionable because plants grow quite slow. So let's say interactively, uh, uh, climbing plants, that can climb on different obstacles, and we used it, as an interactive tool in this case. We have also developed algorithms. This was in 2023 for root simulation, where we simulate different kinds of roots, and they actually interact with different kind of soil, and they absorb nutrients, send them through the three-dimensional structure to the shoots, and the shoot, send energy down there. Uh, we introduce volumetric trees of models where you can actually cut into them and see three-dimensional structure internally, so they are not just polygonal meshes. And last year, we combined the strength model with physics, when you can actually take the trees and break them, and you have splinters flying around, and you can see, beautifully cut three-dimensional structures in it. So following the previous part when I was talking about small plants, these are the developmental and environmental models for trees. Now, there were some advances. The question is how AI can help. And I will talk about two approaches that, after about three approaches actually, that we have introduced, where AI is helping to develop the three-dimensional digital twins of trees. So the first, there is interesting observation that trees grow, by being extended at the tip. So you have the bud, and the bud, depending on the environment, that is the extrinsic part, and on its past, this is, how it grows and where it was, and depending on the actual connection to the rest of the tree. So these are the intrinsics. Based on these conditions, bud will decide what will be the next step. So the next step can be that it will grow, it will stop growing and die, it will become dormant, it will shoot flower, it will shoot leaf, and there are several options that can happen. So what we designed is a new model that we call situated latents, where the part situated means being on the three-dimensional structure of the tree, and the latent means the intrinsic information. And then the key question was, can a neural model learn it? So can we have a deep neural model that will take this information on the tree and will make decision for the bud, what will be the next step? So I already mentioned that the shape is affected by several factors. You may remember that there were three things. One was the the developmental model, that is the DNA, and the second is the environment, and the third I just blanked. But these are the two most important ones. So then again, the question is, if a bot is at location XYZ, and we know something about its history, and we know the environment, can we learn what will be the next action? So we designed, we called it the deep tree algorithm, where you take a node on the three-dimensional space, and then some deep neural network will decide what will be the next action. So we took 8 different species that are on the right-hand side, that is beech, corkscrew, maple, oak, etc., etc. So we have some conifers and we have leaves. We took 500 trees per species, each having several tens of thousands of buds. So we basically obtained a giant data set of buds and their positions. The important thing here is that we took our own developmental model from previous paper that was at SIGGRAPH 2021. Now, what we did, we created a giant database of buds at different locations and its status. So if you look, for example, at bud at the location 1, then what happened is that this has basically grown into 2 different branches. The bud at location 2 grown into 3 different branches with different angles and so on. So we created a data set of a bud at certain location, certain properties, and by checking the status, that is the extrinsic and intrinsic. And then we created 2 neural networks, one that predicts the number of children, whether the bud will die, will branch into 2, will continue as a 1, or branch into 3. And the other network predicts its parameters. So what will be the radius of the branch, what will be the distance it will grow, what will be the branching angle. So we trained the neural network. Now at the inference time, what we do is that we take a bud that is here indicated as an N3, and we run it through the classifier and then regressor 1, regressor 2, that gives us some possible nodes. And then we take the nodes and we put them in the queue. And what happens is that we then we take the node N4 and we run again the same algorithm, and maybe new nodes will be in the queue. And eventually what will happen is that the active node list will become empty, and then we end the simulation. So if you put everything together, then you end up with an algorithm that looks like this. Important thing is that this is not a grow. We don't simulate development. What we simulate is a shape of a tree based on different conditions. What we can also do, we can simulate interaction but obstacles. So you put one node at the root, then when there is occlusion, we calculate light, gravity, and this everything. So when you have occlusion, then the tree tends to grow slightly in different direction, and it will not grow into the obstacle. What we also did, we learned point cloud signature, and then the same algorithm was actually used for point cloud fitting. So we can reconstruct point clouds with this algorithm. And the interesting lesson here is in the big, digital twinning that I was talking about. So we have the developmental model, we have the set of parameters, then we have the input data, and then we have something that is guessing the input data. So in this case, what we did, the something that is there is the AI model that was trained, on bots. But another important thing is that we do not have a plant developmental model here. We actually have a neurosymbolic AI model that is growing this everything. And we also don't have a parameters. So what we basically have, we have an end-to-end neurosymbolic AI model that is learning the shape of the trees, and we have basically gave up all the control. So you just give it initial conditions, some obstacles, and then you run it, and then it will give you approximate shape of the tree. There are tons of validations in the paper. I don't have time to go into details, and it works, but as I mentioned before, it doesn't answer any important questions in science, like what is actually happening inside of the model. The second paper that I wanted to talk about was published actually last year when we were looking at the point clouds of forests. So one important observation is that in forests, many things repeat significantly. There is an interesting claim that trees are actually very low information but high complexity, because you have tons of cylinders that can be somehow deformed, that are branching, but the branching angle usually is fixed, plus minus some variation. And basically then what is happening is that we compose this everything from repeating parts. So the idea that we were following here is that we take many parts that could possibly repeat, and we encode them as a prefabricated connectable blocks. So you can think about it as a Lego pieces that can be connected together. But instead of having just few basic cubes, we have hundreds of thousands of them. So then once we have these connectable blocks, what we do is that we detect them in point clouds, and then we merge them together. So let me explain details of this. This is a point cloud on the left-hand side of a real tree. And then what we do is we find all possible meshes that are in it, that you can see here where I'm pointing with the cursor. They may be even disconnected. So you can see here you have basically 3 cylinders that corresponds to this point cloud. This is beautifully defined, so you have really neat geometry. This is just beautiful cylinder, but as you're getting into the upper canopy, it becomes more and more fuzzy. Now, what we did, we created giant data set of different pairs where you have a point cloud, and then the corresponding parts, they can be disconnected, as I mentioned. And then the algorithm works based on something that is called neural ranking. So what we do is we take the input point cloud, we find instances using the state-of-the-art algorithm. But the important thing is that we really don't care if the instances are not detected correctly. The only thing that we really need is the root of the trees. Then what we do is that we use dbScan, and we basically cluster the individual instances into smaller clouds. And then in the next step, what happens is that we run the neural ranking. So we take each of these small clusters and we find the corresponding pieces that fit into it. So we get initial estimation of the 3-dimensional shape. And then in the next step, we take all these parts and connect them. So we look at the points that were not used, and then we just run algorithm that simulates growth in inverse direction and connects this everything together while making sure that we don't break the topological connectivity, because trees topologically are mathematical trees. So here is an example of a forest that was scanned at Purdue University by our collaborators. And these are the point clouds. And once you get into the forest, we switch into the 3-dimensional reconstruction. We also have a neural network that is detecting leaves in the canopy and putting them there. The last thing that I wanted to talk about are trees and cities. This was paper at ECCV in 2024 when we work with Google, and we use their Google Street View images. So they have many images of individual trees that was actually published at CVPR in the paper that is called Google Arborist. Now the question was, can we get 3-dimensional model out of single images? So we have 2 papers on this, one that was at SIGGRAPH in 2021, and then this one that was at ECCV in 2024, that is called 3D Fusion, where we basically run the fusion model to get initial estimate of a tree. And then we fit it with the developmental model, that is the procedural model, by putting the trees correctly together, and then running multiple simulations of the growth, and we end up with the approximation. I wouldn't call it reconstruction, but we end up with a really good approximation of the trees from a single images. Of course, the problem is that the back part is not correctly represented because there is not enough information in single image. We have reconstructed 600,000 trees, and we use quantitative measures where there were some trees that had measured height, and we also know the height from our algorithm, so it's laying almost on the diagonal with some distribution. The dBH, that is the height at the breast, was also fitting quite well. Now, this can be used for interesting things. So our collaborators at MIT run experiment when they were looking at the thermal comfort through cities. So what you can do once you know the crown area and we know it pretty well, then what you can do, you can estimate the amount of shade and you can calculate, for example, if you go from location A, that may be your house, to the nearest supermarket, what is the optimal path, whether it is important to plant some trees in different areas, uh, or whether what kind of trees should be planted, how tall should they be, and so on. As I mentioned, we have a developmental model, so what we can do, we can simulate the growth of the trees forward, but also backward, so we can look, how the trees would look like if they are younger, and we can look on how the trees would look like if they are older. Now, it is really important that these are all approximations because you don't get very high quality of reconstruction from a single image. An interesting side note is that, as I mentioned, we reconstructed 600,000 trees. It took quite some time. So one tree needed something like 20 minutes on the latest GPU in those days. So on the single GPU, it would take almost 23 years. So the PhD students scrape out, every GPU that was around. We run, on the supercomputer, and I think we spent something like half year running this everything. Now the data set is available. It's on our web if you're interested. It was used in Venice Biennale, where in 2025, where people were able to interact with the tree models, and play with them. So I'm getting to conclusions. What is the take-home message from this is that we need reliable ways to measure plants. Uh, it's actually quite complicated because there is a lot of self-occlusion. Plants are really complicated. They are very tiny structures. They are not the classical computer vision objects that are easily recognizable. We need reliable ways to reconstruct plant models in 3D, and these simulations need a lot more work. So there is a lot of things happening in the communication with soil, with fungi, with plant-to-plant interaction, and so on. And the three-dimensional simulations are really not there. Now, the AI can help, but up to now, we do not have a unified representation of plants. There are, many algorithms that work like isolated islands that simulate very similar things, but it would be really interesting to have, some unified representation for everything. So the closing thoughts are that, machine learning can definitely help us to understand plants better. We need to make sure that we don't give up control. We need to make sure that we use, all the approaches from explainable AI to understand, what the models are learning and what is actually happening there. And the most important thing is that we definitely need cross-disciplinary collaborations. I have learned a ton from my collaborations, and I hope, that our contributions were beneficial. This is the take-home message that I mentioned at the beginning. Computer science is essential in modeling vegetation for science. I want to thank to our sponsors. We are sponsored by USDF and USDA and NSF. I also want to say thanks to all my collaborators, and I also have to acknowledge all my PhD students, and just to show that we actually are not only sitting in front of computer, we also take them to the field from time to time. Thank you very much, and I am ready for questions if there are any.
Okay, thank you very much, Dr. Beneš. Any questions from the audience? I think I can get started with my first question. I'm actually a computer vision guy, and when the first question you mentioned about traditional computer vision and when they do this 3D reconstruction, I always have some issues when I deal with 3D reconstruction problem from the multi-view, which is actually pretty much the traditional computer vision methodologies. And how do you deal with the conclusion problem from the reconstruction? And later you mentioned about segmentation as well for plants and, for example, leaves, and whether they conclude each other, and how do you deal with those problems?
Yeah, many people are working, trying to solve this problem currently. And I think that, having multi-view representation and having giant deep neural models that have been trained on tons of synthetic and real data that have been, manually uh, annotated is a right way to go. I don't think that you can get, enough from a single view because the occlusions, well, you can get enough for a single view if the plants are really simple. If you have 3 or 4 plants and you know the genus of the plant, then, the deep neural model will very quickly recognize the branching angle and the important parameters. And then, it may work pretty well. But as the complexity increases, I really believe that you need not only multi-view, but probably also multi data sources, so combining it with depth maps or LiDAR or something would be really useful.
Yeah, thank you very much. And actually, I'm thinking whether there's something like a good combination between computer vision technologies, no matter it's multi-view or use nerve or 3D Gauss splitting together with some computer graphics and methodologies like what you have introduced in the later.
Yeah, so Gaussian splats is definitely something, that everybody is looking into right now. Now, the problem of Gaussian splats is that, they were initially used for novel view synthesis. So if you look at the image that I have down here, okay, it's a cool tree, with a lot of roots. But if you use Gaussian splats, then you will get some splats on the surface and there will be nothing inside. So if you try to reconstruct it, you will reconstruct really well the things that are visible from this angle. So you would need, multiple angles, but you would also need to get somehow inside. But I know that many people, have been looking. There was a paper at CVPR that is looking at the reconstruction from Gaussian splats. But there are two major problems. One problem is, the self-occlusions. It's really difficult to see what is inside. And the other problem is that plants have very tiny and very thin structures in it. So what you really need is a high resolution precisely on these things. Otherwise, you will end up, with the blurred areas and some weird blobs that are, the common artifacts that we have always seen in these reconstructions.
Okay. And another problem I always have is actually about how do you get ground truth to compare? And I always have this kind of issue whenever I do 3D reconstruction. Some reviewers always say, okay, your ground truth is not the absolute ground truth.
Well, like I think I had it on the previous slide, we need to talk, to people in biology. And like one of the really beautiful things with my collaborators is that, they say, hey, do you need to measure something? We can go and do it manually. And I have seen people washing roots with hoses and then measuring weight and then measuring three-dimensional structure manually. So I think this is one way how you can get ground truth. I would be very cautious. As I mentioned, people are prone to errors. So what you need to do, you need to repeat these experiments. But I think getting ground truth data in biology and in agriculture is really important open problem. Of course, the procedural models can help, and I've been working, with procedural generation of vegetation for 40 years, and I know exactly what are the limitations. Like they are very biased because they are usually targeted at visual perception. We actually ran an experiment when we showed 1 million images. Sorry, we shown images. We had 1 million views of images, and we have created perceptual metrics. And turns out that the procedural models are not as good as we think. So there is a lot of things that could be done in generating synthetic models, and it can definitely help, but they are not ground truth by no means. They can be used for data augmentation, but we definitely need, somebody who would provide ground truth. There is a
Yeah,
question in
thank
chat.
you. Yeah, yeah, in chat. Yeah, I can read it out. And thank you, Dr. Beneš, and for this excellent presentation. I want to hear your thoughts on how this research could help with defining physical properties such as Young's modulus and density in simulators like XXC.
Yeah. Thank you, Yogesh. These things are actually quite easily measurable. So what you can do, you can take branch of a tree, you can put it on some device that can break it, and you can measure these things. And the people have done it. There is a lot of work. So this is interesting. wood is very common structure for building houses and for building structures. So people in mechanical engineering have been studying wood properties from the viewpoint of physics for quite a long time. So, many of these papers are not immediately understandable for people coming from computer science because they have a, very heavy material background. But once you dig into this everything, it's almost infinite wealth of knowledge, with respect to this. So precisely the physical properties are actually something that is very well studied.
Okay, there's another question from Rajisa de Silva, and it's a fantastic presentation. Thank you, Dr. Beneš. Can this model be used to model the seasonal behavior of plants, such as leaf fall and color changes?
Yes. The short answer is yes. The long answer is that, people have been studying the flow of nutrients at different scale. And one of the visually most beautiful papers that I have seen are actually capturing the leaf coloring. So you have, one chemical thing is getting from the tips of the leaves towards the main veins, and the other is going in different direction, and they affect, the color. And it's not only the color, it's also the reflectivity. And the reflectivity is one thing that has been measured in computer graphics by devices that are called goniometers, where you end up, measuring the reflectivity and transmittivity through the leaf. So once you have all these parameters captured, you can plug it into the renderers, and they just generate incredibly beautiful images. So yes, it has been studied. Of course, it's not solved problem. There are still, many things that can be done.
Thank you very much. Any other questions from the audience? I may have my last question. And actually, in your simulation, I saw actually from different branches, and you have actually a set of parameters, and each one has different number of branches. And when you do the simulation, and eventually those simulation, and when you do the generative things, and actually that generates different type of the trees, those coming from the plant scientist, or is something like you observe those difference and when you make the generating models.
Yeah, so when we make the procedural / developmental model, what we do is that we look, into previous work in computer graphics and biology, and many of these models are really well described. So, like, if we talk about trees, I believe there are 12 different basic architectural models that have been described in 19 something, very long time ago. There was a fundamental paper by Philippe de Reffy in 1982 at SIGGRAPH who described and introduced these models. So if you want to develop something like this, you click on one of these 12 models and it tells you the branching structure and branching pattern. And then what you need to do, you need to fine tune the parameters. So if you want to simulate, Apple, then it's known what kind of architecture it is, but the individual parameters is something that needs to be manually tuned.
Okay, thank you very much. Any other questions? So if no further questions, and let's thank Dr. Beneš again. And this talk will be also online and soon our IEEE Agriculture Robotics and Automation Society's website. And we really would like to thank Dr. Beneš again. Thank you very much, Dr. Beneš.
Thank you. Thank you for the questions and, thanks for the opportunity to talk to you.
Yeah, thank you. Have a good day.
Bye-bye.
Bye.
Thank you. Bye-bye.
Thank you all.